So today, this is one of my favorite topic to talk on. That is star formation, and obviously there is like you can say kind of favoritism toward this topic. And the reason for me to show this favoritism because it is something which is like very basic. It like there are a lot of philosophical things you can relate it like we all are dust. We started from dust and we are gonna end into dust. So whatever it is, like you can bring a lot of philosophical point of view for this topic. So yeah, in this talk we will understand. We will basically trace out the journey, like from how everything started. So you will find out that everything started basically with dust. So yeah, that is another interesting part, and that's why if anyone had read this Bhagavad Gita, had read all this, then all this point, even Bible and all. So everything says us we are nothing, human are nothing. They are just descendant of God, like they are just created by God out of some soil. So yeah, we can technically understand that the same concept in more scientific way, more accurate way. If anyone is atheist here, I am sorry to displease him. Okay, so Pogal, next slide. So next slide is like we all know that the galaxy or we all know that universe is not completely vacuum as such. Yeah, though there is a part of universe which is vacuum, but most of the space is between galaxies or most of place inside the galaxies or most of the place between two galaxies, they are not empty. So they are filled with certain particles and they are filled with certain kind of, you can say, atom, very discrete atom. So this medium, here the term interstellar medium is nothing but the as such we know that the medium for sound wave travel is air, right? So here air is what? Air is something which is occupying between source and this receiver. So same as interstellar medium is something which is occupying, something which is present between two galaxies, or if you want to take between two stars, or something which is present between this whole space in order to fill it. So that is what I want from the interstellar medium. So this interstellar medium consists of the gas and dust. So, and we know that one of the most prominent gas which is present in this universe is the hydrogen. Another most prominent gas which is present is the helium. So gas is mainly hydrogen, but also contain element of other molecules. So now, if you ask me what this medium, what I'm talking of, one kind of medium that is interstellar medium. So if you ask me what this interstellar medium is filled of, so basically the first prominent answer will be hydrogen, and that is very obvious because hydrogen is present in the maximum amount in our universe. But there are another elements also, other compounds also, other molecules also, which are present. Now question is from where these elements and molecules came. So these elements and molecules came as a result of death remains of other solar activity. We know that solar system or this whole universe, or you can say whatever you say, universe, solar, whatever you say, I will say outer space. See, this whole outer space is a very violent place. A lot of things are going. So when things are going, it creates a certain elements, it will create a certain molecules. So all these element molecules, they are present in this interstellar medium as a dust, as a gas, and that's that's what I call as my interstellar medium. So, and if you talk what is the density, so this density is typically around 1 atom per cubic centimeter. You can see that very less density. It's very rarer medium. If I am giving you one medium, this is very rare. So basically, this interstellar medium is a theoretical framework. No, sorry, it's not a theoretical framework. It's kind of it's kind of medium which I am trying to put very beginning at of my talk, because this is the fundamental. This interstellar medium is a very fundamental, or you can say very key, or very important aspect for the whole star formation. Because later on you will see that how the star is formed between the with this help of this gas and dust. which is present in the interstellar medium. So Pukal, next slide. Pukal, are you hearing me? Yeah. So this slide. So we also know that this interstellar medium, we can say that they are not very uniform. They also varies with large factors in density and temperature. So I talked about interstellar mediums. So in the previous slide, now I'm saying that interstellar medium, I'm trying to define some characteristic properties of this interstellar medium. So first thing I am saying is these interstellar mediums, they are not very uniform. It's not like if one place the interstellar medium is like this, then everywhere the interstellar medium will be same. They are very different. They are like they varies in the what kind of atom is being found at a particular place. They vary with the temperature. They vary even density. So there are a lot of variation happen. So the clumps in the interstellar medium are cloud or nebula. So now you must have be came across this word nebula, and one of the very famous nebula is the pillar of creation, right? So what happened when this interstellar medium, some place where the density is more, so where density is more, or you can say where density is more, where temperature is in the like in such a range where it can form a clump, it can get collected in certain amount. So that clumps that which is formed, we call it cloud or nebula. So the cloud is very this cloud is very synonymous to the cloud of our definition, what we see in the rainy season, right? What is cloud in rainy season? It is just a certain amount of water molecules, certain amount of this another dust particles, another gases is getting collected together, and they are forming a one clumps, or and these clumps are called clouds. So the interstellar cloud or interstellar nebula, they are the same. They are the just cloud, but instead of water molecules, they are made of hydrogen atoms, hydrogen molecules, and some other compound, and lot of dust. So these are the nebula basically. I hope everyone is clear with the definition of nebula. So now I further this nebula is differentiated into different kinds and different characteristics. There are three types. One is emission nebula, another is reflection nebula, and another is dark nebula. So first of all, we will see what these nebula are, because this cloud, this dust, and this nebula, whatever you say it, you can say it cloud, you can say it nebula, you can say it stellar dust, or whatever you say. You can give your name for yourself also. So this cloud or nebula is a very fundamental to the star formation. It's like it is the key things which result into star formation. So we will try to understand that okay, how many kinds of nebula is there, and what kind of nebula in specific can help in star formation. So there are three kind of nebula in present. Thus you can see emission, reflection, and dark. Pugal, next slide, please. Yeah. So the first is emission nebula. So emission nebula is the very as from the name, those nebula which emit their own light. And why they emit their own light? They emit their own light because of the luminous ultraviolet stars of these stars ionized gas. There are many, as we know that later on you will find out this in the same PPT. You will find out these nebulas are mostly present between the spiral arm of the galaxy. This is stellar cloud I am talking about. They are present between the spiral arm of the galaxy. So we know these galaxies have a lot number of stars too. So what happens? Those sometimes these stars used to ionize the gas in the nebula, and when the gas are ionized, they emit light as the they emit light. And why they emit light? Because once the ionization happens, the electron will go out, and then again to the electron will go to the higher state, and again after some time electron will return to the lower energy level, and this transition from the high energy level to the lower energy level, and again from lower to energy to lower energy level to higher energy level will result into emission and absorption spectra. So this whole process, we emit a lot of this kind of nebula, emit a lot of light, and that's why they are called emission nebula. And why they emit light, I talked about, because the gases in this nebula used to get ionized because of the stars, and then electron used to return from lower energy levels. So they emit a light. I think that's very clear. Google next slide. So another is reflection nebula I talked about. So reflection nebula, as again name suggests, they do not emit their own light. So what happened? They, as we know that if we take a torch and put a light in a dust, so some of this dust will be scattering the light of the torch, right? This is a very simple phenomenon you can see, or you can see at your kitchen, if or kitchen or any window. So when something is being cooked and that smoke is coming out, and if light is falling on that smoke, you can see the dust particles very clearly, and they, it seems that they are emitting their own light, that dust particle. So basically we know that dust particle will scatter the light. So same as this, the reflected nebula do not emit their own light, dust scatter and reflect lights from nearby stars. So the lights are already coming from the star, so the dust particle which is present in the nebula, they will scatter and reflect this light. So this is reflection nebula. So I think we are not much more interested in the reflection nebula and this emission nebula because they don't play major roles in the star formation. What actually interests us, what is major study portion is a dark nebula. So we will see in the next slide. Google next slide. So this is basically a dark nebula. Dark nebula are so opaque that the dust grain blocks any state of the far side from getting through. So what is dark nebula? Dark nebula is like very opaque. They don't emit any light. They neither emit, they neither reflect, they neither scatter. So they are very opaque and they don't emit their light. So if you put any light through a dark nebula, even if there is any star in the behind the dark nebula, you will not see anything because they are so opaque and so said. Now this is the interesting part. This kind of nebula is very interesting to us because this kind of only nebula plays a very important role in the star formation. And now we'll understand why they are like why they are opaque. Obviously, if they are opaque, because first reason, the particles are not reflecting or not emitting any light. Second reason, there is a density is more. The density is more such that light is not able to escape through it. So when I talk light is not able to escape through it, please don't think in the like black hole scale that it is attracting or pulling light hole. Please think low. When I say light is not able to escape it, so suppose if you take a thick solid, like if you take a solid atom, like if you take a brick and you will pass light, you will give some light to it, light will not come to other side, very obvious, because the matters in the solid, that brick is not letting light to go another side. This is a basic concept. So the same thing, and we can understand that matters are much closer, the atoms are the much closest, that's why the light is not getting other side. So this is one of the understanding, and this is a very important nebula play a very important role, and we will see in the coming other slide more detailed about dark nebula. Next slide. So this in this dark nebula, what happens? What kind of molecules or what kind of cloud are present? They are called as a giant molecular cloud. So what happens to giant molecular cloud? What I means to giant molecular cloud is, so what I mean from the giant molecular cloud, so this cloud, there are two senses. One is this cloud is very big. That's why we call it giant molecular cloud. And this giant molecular cloud isn't specific to the dark nebula because first is because their density is much more than the what you saw in the emitting and absorption nebula. And another reason is one more reason, they are more stabilized, they are more electronically, or like the atoms are not getting ionized time and again, and that is one reason. So they are kind of more stable. So we will understand the more basic property of this giant molecular cloud. So we will first thing, they are as I told, this giant molecular cloud or the dark nebula is a very basic of star formation. And that there are some data in this slide, like you can see the typical mass is 10 to the power 4 to the 10 to the power 7. That's what it is, 10 to the power 4 to 10 to the power 7. It is written on 10 to the power 4 to 10 to the power 7 mass of the sun, and the sun is 100%. Density is also given. You can see that density is much more than what I given you earlier. I said density is such that 1 atom per centimeter cube. Like if you remember, like in the very beginning, I told when I was talking about the interstellar medium, I told you that density is very less. That is something 1 atom per cubic centimeter. But what kind of cloud which is interested to which I'm interested in for studying this star formation is like which is some more denser, and this denser cloud mostly are seen in the dark nebula. So you can see the typical mass is from 10 to the power 4. Density is also 100 to 300 centimeter cube, and temperature this 100 to 300 atom per centimeter cube. Temperature is given 10 to 20 Kelvin. Still, temperature is very low. And another one very interesting fact is that if you take the galaxy, so 1/4 of ISM mass in our galaxy. If you ISM stands for interstellar medium, so 1/4 of the only 1/4 of the mass of the stellar medium is our galaxy. Rest is this giant molecular cloud GMC. So we will denoting giant molecular cloud as a GMC again. So again, usually far away distance, uncertainty, they are mostly far away. We don't know exactly distance. They are very uncertain, hard to study in high jet galaxies. Higher jet galaxies, this is a kind of galaxy. This is jet galaxies are the classification of the galaxies, which we will deal later on. So they are not easy to understand and to study in specific jet galaxies, but there are other galaxies which we can easily understand. Next slide, please, Google. So now we will understand more about this GMC. Now we will understand more about this GMC. GMC, as I told, it stands for Giant Molecular Cloud. So the first property of this, like what is the anatomy, what they are made of, how they are structured. So atomic molecular complexes. So these are this particular kind of nebula contain molecules and atom complexes. They are not just simple atom. And the reason for this is temperature. Temperature plays a very important role about the state of particular molecule and particular atom. So as I told, the temperature is very low. So again, because of very low temperature, there are many kind of molecular complex used to exist, and H and S2 due to FeV dissociation. And hydrogen molecules are continuously present, like they are present simultaneously. Sometimes you can see hydrogen as well as hydrogen molecules both are present, and they both are present, and the reason because the dissociation. This is basically FUV dissociation is nothing but if you study the hydrogen and hydrogen molecule cycle, you will come across this term dissociation. This is the basic govern. This kind of dissociation is basic governing factor which regulates how the hydrogen will be transited into hydrogen molecule, how the bond basically function at that temperature. That temperature is a very important part here. So this kind of dissociation only functions when there is a very extremely low temperature. And the lifetime is 20 to 50 m is a million years. So they have a pretty long lifetime, I guess. So 20 to 50 million is again pretty long lifetime. And this in the right side you can see a circle. So in the here, like you can see that 200%, the diameter of the whole circle is some 200%. So this is kind of GMC I am talking about. So in this GMC again you can see some small blue balls. So they can be like molecular clusters which used to form, and their typical diameter range, like here I had given you for 50%, but they can vary. Like if you see these three bubbles kind of hydrogen molecules. So this happens because of this FUV dissociation. A cluster of hydrogen molecule used to form, and this cluster diameters are such that they will be very small, and they will like crowded. They will very crowded, and these clusters later on play very important, like very important. You can say I can say that these clusters later on act as a core of particular star, and I will take you that in later part. So now we understood three things about this GMC. First, I talked. I explained that they are a very denser. Completely, they are very denser. And again, I talked about they are hydrogen and hydrogen molecules complex are present. They have a pretty long lifetime, as well as, and they are the very elementary particle. They are basic unit of the star formation. So now we understand kind of what is this GMC. We understood what is this giant molecular cloud is, and we again understand what they are. We term this GMCs I say your dark nebula also, because dark nebula or GMC or cloud, whatever you say, they are the nearly same. Pukul, next slide. So now the question is where we can find this GMC location. So some are now, as I told, that most of the this nebula are present in the spiral arms. So some are along the spiral arms, some are far away, some can be some are very far away. We don't know, and actually they, as I told, we can't fixate a certain distance to these GMCs, or GMC means giant molecular cloud. So we can't fix, okay, here only we can form. But mostly it is expected they are present at the spiral arms. So in the figure you can see like uh, you can see that this the yellow arrow is there. Two yellow arrows are there. So basically, these yellow this between the arms, you can see there are two spiral arms. Between these spiral arms, the arrow is pointing. So basically, this is the place where this GMC has been observed. And as you told that MSI is seen in 12 CO and visible. 12 CO is nothing but kind of galaxies which has been captured. I don't know where it is exactly it is, but it is the MSI means interstellar medium. Like you can see that here, it is there where the arrow is pointing. So we mostly, as of our study, we consider that this GMC, this molecular cloud, they are present at the spiral arms of the galaxies. And I will tell you why. I think we have already came across this why they are present. Because when we, if you guys remember, when I think everybody was there in the talk, when I was talking about the quasar, I said that black hole is present first, then black hole, because of black hole, the quasar is created. The accession disk is created, and that act as a feed. So when there is a lot of you can see this cloud or dust particle present around this black hole, so we can understand why this GMC must be mostly located at the between the spiral arm, because we know that these galaxies will be present only when there is some black holes, as we studied from the what we studied in the last chapter, last talk, that quasars and black holes play a very important role in the star formation. As and I remembered, I told you I will deal this how this they play important role. So we have that concept tested. So black hole is present only when sorry, galaxy is present only when there is a black hole, and there will be always lot of dust particles circulating that black hole, and this dust particle is basically what this dust and this cloud is basically our GMC, right? They are different types of they can act, this dust particle or this cloud, they can exist into different kinds. Like as I talked, one can be emitting, one can be reflecting, one can be dark. So we all know they all will be collectively present near the black hole, and that's how it makes sense that why, okay, why they will present near the spiral arms, or why they will be always in some galaxies. So this is very I think basics to understand. So till now, what we came across, till now we came across nebula or cloud, whatever you call them. Nebula you can call them cloud, or you can call them interstellar medium, whatever you call them. So we came across what are they, and then we came across how many types of nebula are there, or how many types of cloud is there. How many types of cloud, nebula or cloud, they make same sense. So how many types? So we came across three types, and then again we were mostly interested in the dark nebula, because that is where we are gonna get our star form. So we came to dark nebula, and we later on we started to know it with another name, that is giant molecular cloud, that is GMC. So then we studied the some anatomy of the GMC, means what they are, what they are made of, what is probably their diameter, and then we studied okay where we can find them. So till now, anyone have any doubt or any question they can ask? Like, should I proceed or anyone have any
Yes,
something
please.
to
Yes,
ask?
please. Proceed, please. Yeah.
So till now, this is the basic kind of thing. This funda, like making some kind of concrete ground. So from this, the story of star formation begins. So till now, everyone is clear, right?
Hi there, I have a question. Are these GMCs are commonly called as H2 regions?
Sorry,
Is GMCs are commonly called as H2 regions?
GMCs are commonly called as.
H2 regions, or
Yeah, you
are
GM,
they separate?
No, basically they are separate because S2 regions is that where mostly we observe like 95% of the hydrogen
Yes,
molecules.
yes.
But in this GMC, as I told, predominantly there is a hydrogen gas and hydrogen atom. Sorry,
Okay,
hydrogen atom as well as a hydrogen molecules, and that again they are in the kind of cycle. Hydrogen will change into hydrogen molecules, and hydrogen molecules will again change into hydrogen. But along with that, there are many other remains. These remains are mostly from the dead stars. So
okay.
you can say 90% of composition of this GMC is hydrogen. They can exist in the form of atom or in the form molecule, but they are not just hydrogen and hydrogen molecules. I hope this is very clear.
Yeah, that's fine. That's fine. That's clear. Yeah, thank you.
Okay. Okay, so I'm going to now we will try to understand. So we understood till now, okay, what is generally present in the interstellar medium, what is generally interstellar medium, and what is present in it, and what's its condition, and what is characteristic. We understood this much. So now what we will understand, what we will now understand, okay, from this interstellar medium or from this GMC cloud, what changes or what happens that when we get to star. So Pugal, please go to on the slide. So before that, before understanding, so I'm telling you in this talk, we will mostly look into the basics. Like basics means or very basics like classical mechanics and this thermodynamics, some part of quantum mechanics maybe. So we will try to understand the basic of this, how this star is forming, what kind of mechanism we are applying. So before understanding all this, can anyone tell me that this is a very simple question, which configuration has a more potential energy? Like anyone, there are two
Is it
configuration
A?
in which, yeah, anyone can please.
Is that A?
Okay, you are saying A has a more potential energy.
Yeah.
Can you justify yourself?
Is We have certainly low spherical atomic masses objects having more potential energy than the large
No,
ones.
all the particles are having same masses. Like I think the number of particles are same in both figure, and they are
Okay.
nearly same particles. The only
So might be
difference is
related
one
with the
is
area. Hmm.
no. The only difference in between A and B, one is closely paired, and another is like freely paired.
Okay.
So now just think anyone, or I can reframe my question: which configuration is more stable, or something like that? Because we know that the system which have a lesser potential energy are more stable.
Uh, does A have more binding energy?
Yeah, obviously that's why then only it will be into
It's
smaller area.
so it has more potential energy because binding energy gives it more stable state and all.
No, how you consider the binding energy is more stable?
Because when they stay apart, they have other factors like electrostatic repulsion and other stuff. But when it comes together, even like some other factors may come in and it could give it more stability, maybe.
Okay, so you are saying A has a more potential energy.
Uh,
Anyone else want to try? Okay, so clearly I'm gonna surprise you with my answer. I will say B is having more potential energy and A is having less potential energy. That's why B is less stable and A is more stable. So anybody, I hope no one will agree or someone will.
Like I didn't get it. Can you repeat your sentence again?
I am saying that B is having more potential energy and A is having less potential energy. That's
Okay.
why B is, you can say, less stable and A is more stable. System A is more stable.
Like how does potential energy and stability has a relation here?
That's very clear. You understand this fact that if system has a minimum amount of energy, then the system will be more stable, right?
Yeah.
So energy is inversely proportional to stability. Is system having more energy? What it mean? It is more dynamic, right? And the system is more
Isn't it
dynamic.
like
Yeah,
potential energy and it also has the kinetic energy maybe?
dude. See,
Oh, I'm sorry. Fine. Okay.
see, the thing is, try to understand basic fact. Obviously,
Okay.
suppose, just I'm giving one example. Suppose there is a kid, okay, who is very
Fine.
vibrant, who is like very vibrant and who is like very energyful, you can say energetic. And again there is a one old man who is obviously less vibrant and less energetic, like old man and kid. So whom you expect that, okay, the out of kid and old man, whom you expect that will be sitting one spot for longer time?
Um, maybe the old guy. Yeah.
Yeah, old guy, because he have a less energy. So
Okay.
same analogy happens to the same analogy is being followed for the particles. So if you see that the curve, like the potential curve, or if you go for harmonic oscillator or anything, even the atom, like if you are bringing a kind of electron and you
Okay.
get this potential well, right?
Hmm.
If you, I hope you remember the curve. I'm not having the curve here, right? So if you are
Yeah.
bringing any charge particle near another charge particle, or
Hmm.
like suppose if you are bringing and there is a nucleus and then you are bringing some another possibly charged particle to the nucleus, so you will observe that potential will at the near that will be exactly near to your radius. So that
Fine.
potential, you if you see that the way the most stability is also, it is at the deepest point in the potential well, right?
Hmm.
So that's what I'm saying. And at the deepest point, what happens? Energy is more negative. Like potential energy is basically more negative.
Okay.
So
Yeah.
it means that if potential is very less, the stability is very much more. That make more sense in order. Suppose
Got
if
it. Got it. Got it. Got it.
got it
Yeah.
right.
Please do. Yeah. Yeah.
So I will say that why I'm saying this potential B have a more potential energy. I'm saying this B have a more potential energy because the more amount of energy, like as I told, that general tendency of every system will be to be like if you say what is the general tendency, what does actually system want? So most of the system want stability, and how they can gain this stability? Most of the system can gain stability by having a minimum potential energy. So now if the particle is at a very distance, lot amount of force will be required to make them balance at a particular distance. So here the particles are scattered. So more amount of energy is required to make them stable at that position. However, if you reduce the area, so less amount of energy will be required to this keep this particle in a lesser space. So that's why I'm saying A have a less potential energy and thus more stable, and B have a more potential energy, but less stability. However, I will again, if I hope everybody understood this, but if someone doesn't understand, I will again send a very relevant study matter, and if like on the group, I will say a letter on the group why this happens. So if you any one of you doesn't got it right now, I will get back to you later on the talk. So For now, please believe that A have a more A have a more A have a more stability and less potential energy, whereas B have a you can say more potential energy but lesser stability. So now I'm going to next slide, and that slide we will understand how the basic how this uh, star formation basically happens and what are the factors which trigger this star formation. So I hope in last talk of mine I explained about the causes, and I also explained how this quasar emits Sox wave, how this quarter quasars emits stellar wind, and this is the concept I talked in my last talk. I remember very well. So we will see in the next slide that how they play a very important role in the star formation. So Pugat, please go to next slide. So this is basically a kind of picture slide. So what I want to draw, or I want everyone to draw attention on the right hand side. So in right hand side, you are seeing a series of images. So in this image, the like red color strip is so. So in the first image, what happening? A shock wave that is dominated by red approaches an interstellar gas cloud. So you can see this gas cloud is there, kind of glass cloud is there. So this kind of this shock wave is approaching to this glass cloud. And in the second picture, you are seeing that a shock wave passes through and compresses the gas cloud. And second, you can see that as shock wave passes through this cloud, they are getting compressed. Now I can give you better analogy to understand this. So my analogy works like this. Suppose there is one plane surface, it can be wooden desk or something like that, and there are dust particles sprinkled, like very light dust particle sprinkled kind of uniformly over that surface, right? So there is a wooden surface, plain wooden surface that is smooth obviously, and in that plain wooden surface there are dust particles, and the very light dust particle is being sprinkled. Now what happened? If you blow on that surface, what you will observe? So you will observe that at a certain point, this dust particle will be get accumulated because of your blowing, right? Suppose if you blow that dust particle on the surface, you will observe that density is gonna change. Their distribution is gonna change. So you will see that from the point where you have blown, all the dust particle has blown away, and at somewhat more distance, they will get accumulated, and density at that point will be increase, and this point it will decrease. I think this is a very simple analogy to understand how this shock wave is affecting this interstellar cloud, or you can say how this shock wave is affecting GMC. So as I talked, this shock wave came, and as it passed by, it compressed. And why it here in compression, if you draw a parallel to my analogy, compression means having more density, like density is getting increased and particle is getting accumulated. So now what happens? Motion in the cloud continues after the shock wave pass. So what happened when the shock wave pass? This cloud again start move. They keep on moving. They keep on moving because they are got disturbed. They are got disturbed because of the shock waves. They got kind of energy. Though it started in motion. So once they are compressed, they started into motion. So again, in this image I am saying the densest part of the cloud become gravitationally unstable. So what happened? Like which is more denser, they will become gravitationally unstable, and that will happen. And then what will happen if particle get unstable? What will happen? It will again try to get its stability, and they will start contracting region of gas but to stars. So once the shock wave is passed, the particle get into motions. That interstellar molecular clouds, whatever the particle is present in the interstellar molecular clouds, the interstellar medium, what if the particle is present, they will get into motion. And once they got into motion, the stability or this kind of you see whatever the stability they had, they got disturbed and the particles started moving again. And once the particles started moving, they the particle will start moving and they will try again to get their what you kind of equilibrium, or they kind again they try again to get their stability. And now the question is how they try to get their stability, what are the factors, how they balance this equilibrium, how they balance this stability. And I'm saying this, if you understood how this disturbed molecular cloud, which got disturbed because of shock waves coming from the quasars or some other foreign things. So, because if you understand how they are getting the stability, you will understood how the whole star is formed. So, we will in series in coming few slides, we will understand how the this cloud or interstellar medium, whatever you call them, how this interstellar medium and how this cloud is getting stability once they are get disturbed by shock wave. So as I talked in my last talk, I told us this quasars stellar winds or the shock waves emitted by quasars play an important role in a star formation. So this is the role I was talking about. We know that a dark cloud was present, dark nebula was present, or the dark nebula or whatever you call them, GMC, you call them, Gen Markov cloud. It was already present, but nothing happened till it was present. The key factor or the igniting factor, the things which ignite the star formation was the shock wave. Once the shock waves reach this cloud main, they disturb the whole stability of this molecular cloud. And again, once their stability is disturbed, they try to again get their stability and equilibrium. And once we understood how they are trying to get the equilibrium and stability, we will understand how this star is formed. So in the left hand side picture, you just is actual image which has been captured by Hanixin 206. So you can see this is actually his image that location of his ancient supernova installation. There was here one is I told that shock wave can come from the multiple things. It can come from the stellar wind of quasars. It can be comes from the supernova. So it can come from anything. So I'm not interested from where it is coming. I'm just interested that what impact it is creating on GMC or cloud or interstellar medium. So you can see that arc of compressed by shock waves from supernova. I think the image is not clear enough or you can't zoom enough to exactly see those arcs. However, if you go to the official NASA sites, you will able to get all these images and in a better resolution, of course, and then you can more see. And once in another star formation triggered by compression, as I told that this shock waves is a triggering factor for the star formation. So we will in the coming slide we will try to understand only how the equilibrium is attained. We know that what we know that once this this giant marker cloud will what happen, they are got disturbed and their stability is disturbed. Now what they will happen, they will creating lumps, they will getting dissociated here as in the right side the last image you can see. So they are kind of lumps are getting formed, right? You can see kind of lumps is getting formed. And now tell me what is the most stable shape? Anyone? Like if I give you like sphere, cube, rectangle, cuboid, or if I give you some other shape, so what is the most stable shape naturally?
It will be sphere, right?
Yeah, sphere. So as I said that once the stability is disturbed, it will again try to come into a stable position. So what will happen is as the girl said that the most stable shape will be sphere. That is very true. So what happens? These lumps they are of any they can initially they can be of any side. They will try to get into kind of a sphere ball, and once they got into a sphere ball, they try to get into a sphere ball. The gravity will be start functioning in a different way, and how the gravity will function, that is very important to understand. So we will see in the next slide that how the gravity is function for those sphere size or sphere ball. So Pugal, next slide, please. So in the next slide, I am talking about potential energy due to gravity. So again, I'm just trying. Again, I'm just coming again to back to simple classical mechanics. So we know that suppose if you take a solid sphere of uniform mass m and its radius r. So if I ask what is the gravity of a sphere because of itself, obviously that mass is that sphere is of mass m and uniformly distributed, so that mass will be creating certain amount of gravity. So if I ask what is the gravity of that sphere, what is the gravitational potential energy of that sphere because of itself in a space. So if I, again, you can think of something, I am taking that sphere of mass m and radius r, which is uniformly mass is uniformly distributed, and I am keeping into some space where no other gravitational force is present. So if I ask you what is the potential energy that that sphere is experiencing because of itself, so you will figure out, you can calculate it very easily, that you will see the sphere of mass m, the potential energy of a sphere of mass m radius r will have a potential energy of minus 3 by 5 g m square by r. So this gravitational potential is released as the sphere shrinks. So what happened if the radius will increase, radius will be decreased, what will happen? Radius will decrease, it means the value will be, this value will be increasing. Will what it means? It will means the potential energy will become more negative, right? If radius is increasing, the potential energy will become more negative. And what means that if the potential is more negative, it means that potential energy is getting decreased. As I told in the beginning, if the energy or potential energy of the system decreases, the stability increases. So that's what it is said. Gravitational potential energy is released as sphere shrinks. That is very important. As we can see that if R decreases, gravitational potential energy become more negative. And once the gravitational potential energy become more negative, what does that mean? It means that the system is getting more and more stable. So now tell me, so what is the general, what is the natural, what will happen naturally if I am taking gas ball of radius certain r and keeping it. I'm not thinking of any other forces, any other effect. I'm just taking a sphere ball. I'm saying there is no other force exists in the universe. There is no other force. Only one force is there. That is gravity. And that gravity, I'm just keeping it and keeping one sphere ball of gas or something like that, and keeping in a universe space. I'm just giving you ideal condition that there is no any other force. So what will happen? The sphere ball will be start shrinking. Why it will start shrinking? It will start shrinking because by shrinking its potential energy is going to decrease. Its potential energy is going to release, and if this potential energy is going to release, it will become more stable. So this is the my analogy. Why I told that the one I asked you earlier, that which have a more potential energy, right? Initially, I asked you one question which have a more potential energy. So now I hope that is very clear to us that why the B was having a more potential energy and A was having a lesser potential energy, because radius play an important role. If the system has a very less energy, means it is a more stable. So general tendency of any system, if there is no other force, remember the condition, if there is no other force present, is that general tendency will be it will shrink and it will shrink and shrink. It will shrink such that till the point that it will have a minimum amount of energy. So that is the general tendency we have to understand. And why this is a general tendency? This is a general tendency because every system wants to have a very minimum amount of energy with itself, and that's the reason why, that's how they can get stability. So every system want to stable, and they can get this stability because they want to have a minimum amount of energy. So if what the sphere ball will be do of mass and radius r, it will try to sink so that it will have a minimum amount of energy. I think this is very clear to everyone, and this is the one of the very important formalism to understand the star formation, and I will explain you how that is gonna work. So Now if you ask me from where I am getting this derivation u is equal to minus 3 by 5 gm square r, that is mostly that is actually known as a gravitational, sorry, it is known as a gravitating potential energy of an sphere. And this is a topic in class 12, I think, not class 12. This is topic of bachelor BSc degree. I studied in my BSc courses. So I think that is UG level topic, and that you can find, even you can find it in the Kittel book. Google, next slide please. So this, as you can see that is this is a derivation in this slide. You can see the derivation, how I am deriving it. This derivation itself is taken from the Kittel book. So you can find the sphere gravitational potential energy. You can go and refer to the Kittel book or any other standard book, or even you can type on the internet and figure out. And you will find this very beautiful formula which explains that why a sphere ball, if there is no other force is present, why it will try to swing. So, and basically this formula, under this very beautiful formula and concept play an important role in the formation of stars. So now what will happen? So, Pugal, can you go to the last slide? No, you are going forward. You go back. This one. That next slide. Previous. One more previous. Yeah, this slide. So now I hope I am again coming to this. So suppose these are the two spheres, and this green balls, they are kind of gas molecules or dust molecules or dust atom, whatever you call them, which are present in the form of sphere in a GMC. GMC is giant molecular cloud. And what will happen, because of this formula I told you, they will shrink. They will shrink. And why they will shrink? They will shrink because they want to get more stability. So with my formula A is a more stable. So the same you apply to the giant molecular cloud. As I told that in a universe or during this nebula, there are a lot of dust particles are there. And because of this disturbance, because of the disturbance of created by shock waves, they got into kind of sphere shape. So now in order to attain the stability, what they will happen? They will keep on shrinking, right? So they will keep on shrinking, they will keep on shrinking, and they will keep on shrinking. So now you can understand the general tendency of that spherical nebula or spherical cloud, dust cloud. What is their general tendency? They will make a sphere shape and they will start shrinking. So now question is, till when they are gonna shrink, or what is gonna stop them from shrinking, right? Because obviously they can't shrink to a zero radius, right? So if I'm saying you, if they will keep on shrinking, so obviously they can't shrink to a zero radius. So now it is very important to understand what is gonna stop them from shrinking, because they have to find equilibrium finally. And this, once they found the equilibrium, the stop will be formed. But and how they are gonna find this equilibrium? So obviously, Pugal, next slide. Again, next slide. Yeah. So we know that this gravitational potential energy is being created because of the gravitational force. So gravitational force is directed toward the what? We know that any gravitational force is a central force, so it will be directed toward the center, right? So this force will be directed somewhere near the center. So now we know that the gravitational force is directed toward the center of that sphere. So in order to create equilibrium, in order to stop to shrink it for zero radius, there should be some another counter force which should be creating from that sphere. So now what is that counter force? So we'll try to understand that in the coming slide. What is that counter force which is acting from to this gravitational force? So which and and we will try to understand how the equilibrium is being created between this gravitational force and that counter gravitational force which comes in very basic way. So Pugal, next slide. Pugal, can you listen? Yeah, this slide. So now my question is, which cloud will collapse? So the thing is, I told you that every cloud will be in a spherical shape after some time, after the shock wave passing through it, and they will start shrinking. So now the thing is, which cloud will collapse? Like which collapse in the sense, which cloud will be getting into keep on shrinking, collapsing in the sense, which cloud is gonna keep on shrinking. So till now we understood that gravitational force cause object to collapse. Collapse means shrink. Like we know that because from the formula of gravitating sphere, we know that a gravitational force is gonna cause object to collapse. So what keeps object from collapsing? So what is the thing? What is the thing which prevent object from collapsing? What is the thing which find equilibrium? That is a very important question. And so we will try to understand. So as we can another develop another analogy in the solar system, the motion of planet keeps them from falling to the sun. We all know that if there is just a planet and sun, the obviously the sun's gravitational pull is much more stronger. So it will pull that planet to the sun, and finally the sun planet will fall into the sun. But that doesn't happen because in solar system motion of planets help them not to collapse. The motion of the circular motion of the planet help them to keep on equilibrium distance, like they maintain equilibrium. So what happens something like whether something same happen in the star form during the star formation also? So answer is yes. So we know that in a gas, the random motion of the gas atom can support the gas against the gravity. So I was asking a force, what is the force which act in counter to this gravity? So that is force coming from the random motion of the gas. We know that this interstellar cloud, they are made of the gaseous particles, they are made of lot of dust particles. So these particles are not stationary, right? They are got into motion because of the shock wave, as I told before. So this random motion of the gaseous particle can support the gas against the gravity, and how they are supporting. So now we know that if the particle is in the motion, they will experience? They will experience friction. There will be collision and friction. And because of this continuous collision and friction between gases, two or more gases, they emit amount of thermal energy. They emit this, we know that kinetic energy or this friction will create a heat. So this they create they emit thermal energy, and this thermal energy will result what? They will further result into the expansion of the gas, right? So suppose what you can understand it this way. So now, if there are a lot of gases there, and the gases is being heated, what is their nature? They will expand, right? So the gases will be expanding, and what is gravity is doing? Gravity is causing the shrink. So now we got a counter force of that shrink. That gases will be expanding, the gravity will be shrinking. So at a point, we expect that a equilibrium will be reached because gases internally are expanding, and the gravitational energy, because of the gravitational energy, the whole ball of the gas is shrinking. So now these are the two counter situations. Sorry. Now these are the two counter situations which we came across. So this is the counter force I was talking about. So what is the counter force? Now we have thermal force which being exerted because of the random motion of the gas. So again we understand. Till now we will again understand this chronological development. So the chronology, as chronology says, the first, the gas will be in the sphere shape. Because of its sphere shape, its general tendency due to gravity will be shrinking, but there are a lot of gas particles which is in the random continuous motion, and because of this continuous motion, there will be friction, and because of friction there will be heat, and because of heat the gas will be expanding. So this expansion will oppose the shrinking of the gas. So this is very clear. So now anybody have any like kind of confusion or doubt or dilemma in understanding this chronological development till now which I established? So anyone please have, if please bring it up. Is it clear to everyone?
Yeah, I think yes.
I hope to everyone, not just you. Okay, fine. No one is responding. Maybe. Okay, fine. Uh, okay, I'm moving to next slide now. Pugal, next slide, please. Yeah. Yeah, this slide only. So now I came across these two forces. These two forces I came across. One is gravitational forces, and another is this thermal forces, which is acting from inside, and they are creating a thermal pressure from inside and result into their expansion and acting opposite to the gravitational. So now what is the total energy of this gas cloud? So obviously this total energy will be because of the two factor. One is this gravitational potential energy, that is because of the gravity, and we know that because of gravity U is equal to minus 3 by 5 g m square by r. Another is another force which will happen, another energy which will get is the kinetic energy of an atom. So n atom means there are lot number of atoms, I don't know. So the kinetic energy, we know that this is a formula which we came from, which we know from thermodynamics. So kinetic energy is equal to n 3 by 2 kBT. I hope this formula is clear to everyone, because this is a very simple thermodynamical formula. Where 3 is what? 3 is nothing but this is 3 is what? 3 is degree of freedom of gases, because we know that the thermal energy, thermal kinetic energy of any gaseous particles is equal to n f by 2 kBT, where f is what? F is your degree of freedom. So this formula is coming from that only. This is very basic formula, and we tell us what is the kinetic energy of gaseous atom which will present when they are in a continuous random motion. So they will be n 3 by 2 kBT. And next part, just n is expressed in the terms of mole numbers, that is total mass into molar mass 3 by 2 kBT. So that doesn't make much differences. So the total energy of this gas cloud will be the sum of these two fundamental energies, that is gravitational potential energy and the kinetic energy. So if we oversum this two energy, we'll get the energy of the gas cloud. So next formula, next slide please, Google. Google, are you listening me? Yeah, this slide. So as I told that the total energy will be m by mh 3 by 2 kBT minus 3 by 5 gm square by m. So now there are two conditions, whether my total energy will be less than 0, another will be total energy will be greater than 0. So now with the question, the bigger question which we have, that whether the every system which been created, where the two diverse or opposite forces being acting, one is the gravitational force which is trying to shrink, another is your thermal force which is trying to expand. So whether the system which is created under these two opposite forces, whether in this opposite forces, whether the every system will survive, like every system will find equilibrium. The question to answer to this question is no. Every system is not gonna survive, or every system is not gonna find equilibrium. Only if system total energy is greater than 0, then only a gas cloud can support itself, right? And that is very, I think that we can understand why. Suppose if total energy is greater than 0, means the first term is greater and another term is less. So if the first term is greater, it means that that term, that thermal expansion, is countering that gravitational energy, and the system will not shrink finally, and that system will not shrink. That is a very basic things to understand. So as I told, natural tendency because of gravity is shrinking of that sphere. So there is a force which is acting opposite to is the thermal friction, and the thermal force should be such that it should be either equal to zero, E is equal to zero, or E should be greater than zero. So that's what I am saying. If E is greater than zero, then the glass cloud can support itself. It will not sink. So density of glass cloud is N. So here again, I am finding the density of the gas cloud. So total density of gas cloud is equal, M is that is N. So then you can find the mass, that is equal to, we know that mass by volume is equal to density. So that this formula comes basically from mass by volume only. So volume will be 4 by 3 pi r cube. So this is your volume, and mh here, as you can see that I'm predominantly taking the mass of hydrogen atom only, because they are the predominant, like nearly 90% of the hydrogen atoms what constitute this GMC. So for my easy calculation, I'm taking this thing. So I hope this is clear as of now. So we came to know this thing. We came across the two different kind of forces, how they are acting, how one forces is countering another forces. We came across the different energies because of these forces, and then with the help of these different energy, we were able to find the total energy of this cloud. So now this another is, we'll try to implicate all these ideas what we had developed so far in understanding the star formation. So next slide, please, Google. Yeah. So protostars. Now in this, we are trying to understand the same concept what I had been telling you in a more different way. So again, this is kind of lump, kind of. You can see that clumps are like, what do you call them? Lamps, clamps? No. What do you call them? Oh, I forgot.
Lumps.
Yeah, lumps. Okay, fine. So this is kind of lumps, and because of the self gravity, as I told, they will be like shrinking. As you can see that the gravitational forces will be, will be toward the center of that lumps, so it will keep on shrinking. Now what will happen? Now after this, it is like, if you see, always the stars are not formed on the like one. It's not like stars are not formed individually. Stars are formed in a group, like we mostly get binaries of stars, or the clusters of stars, or something like that. So why that happen? Because once this bigger lumps is formed and they keep on shrinking, they further then they used to break down. They break down into smaller lumps, they break down into smaller pieces, and these pieces again go into the same process of shrinking and expand, like same things I talked about. So this and these, then they result into protostars. So what is that protostars form? Protostar is that it is the like kind of very first stage of the stars which is formed after from this molecular cloud. So protostars formed by collapse of molecular cloud. So the cloud must be dense and cold. Clumps are coarse to collapse. So as I told that, the first thing, they should be dense, and they should be very cold also. The temperature should not be much. Anyone can tell me what happens if the temperature is more? Like anyone?
It tends to sink further.
Sorry, I didn't get you.
Like it goes on shrinking
No, if
without
I'm saying
any
if
counterflow.
no, if temperature is more, temperature is
Okay.
more, not less. Temperature is more.
Okay.
It will
Then
expand.
the reverse happens.
Yeah, exactly. So the thing is, if temperature is more, the expansion will be much more than the. We know that gravitational force is basically kind of weaker force when we talk into the molecular and atomic level, right? So when the temperature will be more, the expansion will be happening more, and the contraction will be coming will be less. So they will know equilibrium because because thermal expansion will be there. So the gas can't be compressed or they can't be shrink, and then density can't be increased. So if temperature is more, density is gonna be less. So that is the thing why we can't afford a higher temperature for the star formation. So that's why I'm saying that cloud must form a dense and cold clumps are cores to collapse. So this is the core lumps. So typically multiple stars form from one gas cloud. So we know that why this multiple stars are formed, because this clumps what I had talked about, they get fragmented, and the same process is repeated in every fragment. So Pugul, next slide please. So this is one of the image which was captured by your Hubble Space Telescope, which shows the procedure of formation of stars. So in the center you can see the bright spots where there are a lot of lumps are there. Suppose if you again you can't zoom it this image for better resolution. I am sorry for that. But if you zoom it and figure out if the image is of better resolution, you will see that there are a lot of lumps is being formed, and these lumps basically every lumps will result into a cluster of stars or cluster, and that cluster or you can say many, and that's why we call it as a nebula. So nebula is nothing but
Samarth, we can't hear you.
Yeah, I can't hear him. I thought it was
No.
my connection problem. Can you hear us? I think he just text him now. Wait, I'll text him. Nope, he's not responding. Samarth left, it seems. I don't know, he left. He's not showing his. Good, good.
ये तो बढ़िया नेट चल रहा.
Yeah, we can hear you now.
You can hear me?
Yeah.
Okay. So what was the last slide I do? I talked about Genesee satellite one, right?
Yeah.
Okay. So
We can't hear you, Samarth.
okay. Just give me a minute.
Samarth, say something. I think you muted yourself.
Can you hear me?
Yeah, I can hear you.
Okay, fine. But I'm not able to see that PPT. Am I audible, right? Okay, so just go to the next slide of that NSG image, SST image. Are you there? Okay. I can see. I don't know why it's still loading, but I'm able to listen you all. Yeah, I will carry on because anything is. So, as in the slide, you can see that this self, as I told that the cloud will fragment, right? So, as I told that as the gas and dust falls in, it picks up speed and energy. It is slowed by friction, and the energy is converted into heat. So, as I told that once the particle will start collapsing and it will start shrinking, this sphere is start shrinking. So what will happen? The particle will be getting speed. They are in continuous motion. So what will happen once the you are compressing? As we can understand this in a more simpler way. If you take a sealed container and you are compressing the gas in that container, what will happen? What you will observe? The gaseous particles are moving in a more erratic way. And why that is happens? Because we know that PV is equal to constant. So if you are if you are decreasing the volume, and then what will happen? Pressure will increase, right? Are you able to hear me, right?
Yeah, we can hear you.
Yeah.
So now we know that once the volume is reducing, the pressure will increasing, right? This is a very simple thing because kV is equal to constant. So once what happened, the same thing is happening at the star level formation also, like at that level also. So once the star, this gases, big gas molecule, they keep on sinking because of this gravitational pull, or you gravitating self-gravitating power. What will happen? The particles which will be picking up more speed and more energy because the pressure inside is increasing, right? We can again understand it in a very simpler way, that if you keep on pressing at a particular point, what you will see, a kind of force, more amount of force is being exerted at that point. So that more force, kind of this simple thermodynamical analogy and understanding, that will help you to understand once the gaseous particle is being so that sphere of the ball sphere is shrinking, the gaseous particle will pick up speed energy. And how this energy, again, everything should not go to limit. There should be some limit where should be checked. So it is slowed again. It will slowed automatically by itself, and it will slowed automatically by itself. Like they will know no other thing. It will slowed by friction, and the energy is converted to heat. So they will heat, and that heat will be, as we know that the particle will keep on colliding. That of because of collision there will friction, and because of friction there will be heat. So as long as the protostar is transparent, the heat can be radiated away. So again, I started my whole things with a dark nebula, right? So we know that as long as the protostar is transparent, the heat can be radiated away. So if I had been taking the emitting nebula or this reflecting nebula, so it means that my heat energy will be radiating away from the spherical cloud. That's why I took a opaque nebula or dark nebula, so that heat can't go out. Heat should get trapped. So as long as that's what I mean, That's another justification why I am more interested into dark nebula, because in dark nebula only the heat will not get radiated. So when the protostar becomes so dense, it is opaque. When the heats the buildup, the pressure increases, and the rapid collapse slow. So now what happens? So when the heat at the core means at the center, the heat will be increasing, the pressure will be increasing, right? So that sinking process, which might be happening earlier at a much more rapid rate, now it will slow down. Now it will stop, or it will be kind of reach into equilibrium, and it will be slow down, and that collapse which is happening, that sinking phenomena which is happening, it will slow down. So Pugal, can you go to the next slide? Are you able to hear me? So you are in a slide. So now the gas in the cloud keeps falling onto the protostars. So we know that initially what happened, this gas is getting more and more gases. See, the thing is, once this phenomena is ignited, the more and more gas will be getting accumulated because of the gravitational pull. So we know that that sphere of ball again will be having much more depth. So what it will do, it will attracting other gases of the region also. So gas in the clouds keeps falling out of the protostar. So more and more gas will be coming, and the more and more gases will going to the core. So it's not that the surface gases will remain at the surface. So the surface gases will go to the core, and because of this as it falls in the formation of the protostar, so what will happen, these gases will go more to the core, and because of the more as these gases will get more core then the temperature and pressure at the core will be increasing. So once this gases reach to the core, there will be high temperature and pressure, and because of this high temperature and pressure, they get ionized. And because of this ionization, what will happen, they get electrically charged. Now, once they get electrically charged, they are moving in a continuous direction, and because of this movement, and we know that movement of electric charge will give us a magnetic field. So, because of this continuous motion of this ionized gas particle, will generate a magnetic field, and this magnetic field will be twisted, and then because of this, we will get a much more stronger solar winds and other phenomena. So this protostar keeps contracting under its own gravity. The protostar is powered by gravity via contraction, not by fusion. So till the protostars, there is no ignition of this fusion, or this reaction, what is which gives power, that is fusion reaction. That doesn't happen till now, till this stage. What is being fueled, what is being happening is that it is automatically that gravity itself is compressing. Gravity is compressing, the gravity is developing this pressure, this temperature, and this gravity is only fueling this protostar. Till now the fusion is not started, because we know that in order to start the fusion, we need a very high temperature and very high pressure. Still we hadn't reached at that level. So the protostar keeps contracting under its own gravity. The protostar is powered by gravity via contraction, not fusion. So it is very basic and important to understand that this whole thing, the whole formation thing, till from very beginning, from dust to till protostars, the thing which is fueling this whole formation is gravity, nothing else. So the protostar becomes stars when it is contracted so much that it is dense and hot enough to begin nuclear fusion. So the transition between protostar to stars happens when, as I told, that the gravity will keep on getting more and more atoms and more gases molecules from the surrounding. And once the more and more atoms and molecules are getting accumulated in the surrounding, the more and more pressure and temperature at the core will be increasing, right? So because that again can be very simply understood. Suppose I think I had already given this example. I think I had given on the discussion also. Suppose if Pugal is in the mid of something, and more people are climbing over him. So suppose first there are some 50 people, again 100 people came over him, next 150 people came over him, next 200 people came over him. So now ask what will the condition of Pugal? Pugal, what will be your condition? So basically, Pugal will be top, and he will also facing a lot of heat also because though Pugal will be facing completely lesser heat than what those gaseous molecule will be facing because there is no friction in this case. So anyway, he will facing more heat and pressure. So that's what happened because of this gravity, because of this gravity of that sphere which formed initially because of that shock wave, it will keep on pulling more and more this clouds toward it, and this more and more cloud will develop more and more pressure and temperature at the center, and at a stage will come where the temperature and pressure will be enough to ignite a nuclear reaction and to ignite the process from where the hydrogen will be changed into a helium. So this is the thing, and the time when this nuclear reaction is ignited, then quantum mechanics come into play. Then from protostars to stars, we till now we had just formed the star. We are not going to study at what happens after the formation of star. So these are the principles which stars involved in formation of just stars. Like we are stopping at here only. Will not go beyond because beyond you will deal with quantum mechanics. I think we have enough time. Or we don't have. We have time or we don't have. Pavel, can you reply to that?
It's actually 5:37.
Oh, okay. We are off time again. So I think again for me time is a big problem because I always used to get short of time. Okay, no problem. So this is my last slide. Go to last slide, Google.
I'm there.
Well, like slide number 25, the last slide, right? Are you listening me?
Yeah.
Yeah. So I'm skipping some materials in between because I have already eaten up a lot of times. So, but those materials are not much. I'll share my this PPT in both platform if you have any doubt. So till now we had understood in this talk what is the roles, what is the like two principles basically gravity and this thermodynamics or classical mechanics of thermodynamics, how they help us in forming the protostars. We had only understood how from a dust the protostar is formed. We have understood how a lot of things by someone. If someone is not taking up slot, I will again take up and we will further try to understand the condition under which the star will forms. So I think we are pretty much clear with the answers. What are the conditions under which the star will forms? So we came across we should have certain triggering point. And what is that triggering point? It can be kind of shock which can just disturb this your giant molecular cloud. So this triggering mechanism is very
Shock
important.
wave,
Sorry.
like the shock wave example.
Yeah, it's a good example. So now another thing which we come to know, which we would like to know in more detail, is these type of interstellar clouds are most likely to form stars. Again, we have a kind of answer for this. So the kind of answer which we have is dark nebula, or the one which have a denser, which is colder enough, and which are present somewhere near to certain black holes or at a position where these waves or shock waves or this struggling factor can impact them. So now, which location within the clouds are most likely sites of the star formation? So again, this is the thing which we didn't came across, and I think we will talk again somewhere because already I took some 1 hour 40 minutes, I guess. So so which location? Because the cloud is so big, as I told that the size of the cloud belongs like it's in parsec, it's very huge. So in the whole cloud where exactly the star can be formed, and whether star formation is spontaneous or whether it needs some outside trigger. So again, we know this answer. The star formation is not spontaneous. We need some triggering mechanism, and that triggering mechanism is again that's all. So this is why my last lecture on the quasar was very important, because this quasars and this black hole and this shock waves, they all play very important kind of very important impact in the whole star formation. And because of those black holes, now you can be more thankful to the black holes that why we exist, right? So kind of we are thankful to the black hole for our own existence, because if the black holes is not there, most of the things, most of the triggering mechanism would not have been there. So as I talked, this I talked very clearly in my last talk. So in this talk, we understood a bit more, that we understood okay how protostars are formed from the dust. So I think that was the end. Now if anybody have doubt, they can